Okay, so today we are going to essentially speak about generative models from the place where I had left in the earlier one, and this is to continue with exactly like how you can train a generative model so that it gets working in the most proper way. Okay, now here what would happen is that we make use of one of these kind of special architectures called as adversarial autoencoder. Now, the whole concept of an adversarial autoencoder is that you will bring in the concept of adversarial learning in order to train these models, and the whole model is like an autoencoder. So, in the last class, I had spoken about the point that there is a special class of neural networks which essentially have this property that whatever you give in the input, it can produce the same thing on the output. And if this is a condition where you don't have any kind of a bias associated over there and there is no nonlinearity, then that could essentially end up becoming that the neural network is going to do eigenvalue decomposition on some sort. So it's essentially like uh, whatever is the weight matrix from the input, which is x, to this latent variable, which is z, that matrix over there, inverse of that matrix is what will in that case bring z back to x, or in our case that will be x hat, or just an estimate of x and not exactly completely x. And the reason for that is that if z is smaller, the number of neurons in your z, which is the latent vector layer over here, is lesser than the total number of neurons in x. In that case, what happens is a lot of information compaction goes on. So essentially all the information cannot be carried forward. So you will have some of these information which gets compacted or is lost in the whole process. So that cannot be recovered anymore. Nonetheless, if the total number of neurons in X is the same as total number of neurons in Z, then you will have a 1:1 correlation between them. And as a result of this 1:1 correlation, you would find out that this ends up becoming just a identity transform in some way. So in the best case, it should be an identity transform. Now, uh, what we are doing over here is you would assume that this is a very generalized neural network, and for a generalized neural network to work out, what should also be there is that there will be bias and there will be nonlinearity. It has to be a realistic one. So when you have a bias and nonlinearity present over there, then all of your matrix transpose or inverse policies and others will not be working out that straightforward. So now here the whole idea is that I take in my input variables, I give it to the neural network. This has two hidden layers, and from there I bring it out to this intermediate layer called as Z, and that number of neurons in Z is less than X, and that's the point when you will also get down a compression coming into factor. Now there can be two ways of training this whole thing. One is and in fact, like there has to be two different ways of doing it. So what you do essentially is that initially you would do a backpropagation with minimizing the loss between x and x hat. X hat is whatever is predicted as in over here. Okay. So now if I'm minimizing the loss or a mean square error between x and x hat over there, then that should be good in order to train this one to behave like an autoencoder. But then we did realize that that is not going to get hold of any specific statistics which this z should be following. So z in this case is going to asymptotically follow qz, or the distribution of z. Now that is some distribution, so we don't exactly know whether that is a well-known distribution or not. Now what we wanted to see is that will this qz be very close enough to pz, and in that case what we can say is that if we are drawing a sample which comes from a distribution like pz, then by virtue of the fact that qz is similar to pz, like qz as a the distribution of z over here as observed is the same as what will be the distribution of any randomly drawn variable z from here, then we would be able to see that whatever is produced on the output is going to look very realistic. Okay, and that becomes the essential part. That is what we want to achieve in any way over here. Now the point is that now that I want to achieve all of this, the question is that will I be able to do that appropriately? So for that, what I will have to do is that I will have to ascertain that for every single time there is an actual x going over here, the output looks like x, and also ascertain that whatever z it is producing whenever there is an actual x going over here is something which follows this distribution pz. And for that, what we are doing is an adversarial learning route. So there we bring in this next neural network at the bottom over here, to which what you are going to do is you either give it a random valued sample drawn from pz, or you give this actual value of z which is coming up. So this whole thing knows whether this whole thing does not essentially know whether it's coming from here or there, because there is this input block which is essentially a flipper. So it's a switch which randomly flips between whether it's coming from qz or it's coming from pz. What you would like this neural network to do is predict whether it is coming from qz or is it coming from pz. So the job of this neural network is just to predict the state of the flipper over here. And in order to predict the state of the flipper, the only thing it is given is either this or this. So it has to look at the value of z and say whether it's coming from here or it's coming from here. Now, in the event that the distribution over here is very different from the distribution of variables over here, this whole thing will be able to learn it very easily. So take an example. If z is just a one-dimensional number, it's a one-dimensional scalar value you are putting now, then what will happen is, if say this pz, and pz is a Gaussian distribution with zero mean and unity variance. Now if qz is some sort of a Gaussian distribution maybe, but it has a variance of 10 and a mean of 100. Now in that case, most of the numbers which will come from pz will be somewhere centered around 0 and mostly varying between plus minus 1. Whereas pz, which has a variance of 10 and a mean of 100, will have its values centered more or less around say 90 to 110. This is what will happen. Now most values, whenever they come from 90 to 110, this network will be able to tell that this is coming from here. Whereas if most values come between the range of plus minus 1, then it can say that it is coming from here. So this is where this disparity in distribution will help this network actually predict from which distribution is it coming. Now, when do you think this network over here, which is the discriminator, will start to get confused whether it is coming from pz or is it coming from qz? So you can write the answer. When do you think that this discriminator network over here will get confused that the random number is coming from qz or is it coming from pz? So you can write it on the chat box. Under what condition of qz and pz will the discriminator get confused? Yes, Avijit says that the mean is very close. Yeah, mean is very close, or and can you have something from the variance? So say both of them become zero mean, but qz has a variance of 10 and pz has a variance of 1. Will it still be possible? So qz has a variance of 10, pz has a variance of 1, but they all both of them have the same mean, which is zero mean. Do you think that is possible? point is in common variance region. Yeah, so if the point is in common variance region, it cannot. But say you have a series of random numbers which are getting generated, say from Pz, it is going to be generated in the range of plus minus 1, and Qz it's going to be generated in the range of, majorly in the range of plus minus 10. So you mean to say whatever is there in the range of plus minus 1, it is going to get confused. But if the number is say in further of ranges, then I don't think it is going to get confused. Did you get my point? So if you get my point, then you can write down something on the chat. So the question is very simple. So if this QZ and PZ, they are somewhat different, still this discriminator can make it up. But then if both of them are very similar to each other, in that case the discriminator does not really have any role to play, because the discriminator will not be able to discriminate. So if QZ and PZ both are zero mean unity variance, or both are say mean of 10 and variance of 100, or mean of 100 variance of 10, in that case it will not be possible. Now the only condition which will help you understand this one is that if this whole thing over here, this discriminator network over here, can be made to be confused, if you can get that one confused, in that case there is no challenge. So essentially now it can work out very good. So now the point is, how do we get to have this one confused? So who is going to confuse this one is the question, because this random sample which I am drawing from here, that is not changing. So this is a fixed distribution which is given. The only thing over epochs, as it keeps on changing, is this network and the weights over here, which is basically my encoder and my decoder. So if my encoder modifies itself, modifies its weights in such a way that QZ, that Z which comes from QZ, and then QZ becomes very similar to PZ only, then this will be confused. So now in some way the loss or error of this network or the discriminator over here, I need to tell the state of loss of this discriminator to this encoder in some way, and only in that case will this encoder be able to modify itself such that it starts producing these Zs which will confuse this discriminator over here. So that's my primary role, and that's my primary goal. That's what I essentially want to achieve through all of this. Are we clear with this? Are we clear and good with this? So students, if you are having problem, if you are not able to understand any part, you joined in a bit late or some issues, then please write it in the chat box so that I can understand where you are stuck, and then I can revise that part. Okay. So the last concept over here was something like this, that see, my job is to make this QZ resemble PZ. That is what we had done in the last class. And the reason for making QZ resemble PZ is that now if I draw any random number from a distribution PZ which is well known to me, then it will produce an X hat or output over here. So just look into my screen, like have that one completely shown, so you will be able to see. Now then it will produce X hat over here, which is something which very closely resembles X or will be very realistic. Now what that would mean is that I need to produce QZ which is very similar to PZ. Now the point is, I don't have a direct way of imposing that on QZ. So what we do is we take hold of this neural network over here, which is called as a discriminator. And the job of this discriminator is to make that happen. But then how we do it is through an indirect step. So what we do is we have an input block over here, and this input block, this block which says itself as input, this block is something which has a flipper kind of an arrangement. So either it can pass from this axis Z, which is vertically above, or it can pass from any Z which is drawn from a random value distribution PZ, and then it goes into this discriminator. Now the job of this discriminator is to predict whether it has come from here or it has come from here. This is the only thing which the discriminator has to do. Now what we are trying to do is the only time the discriminator will be confused. So this is what I'm predicting out. The only time the discriminator will be confused over here in its capability to predict whether it comes from this vertical line or from the horizontal line is when this QZ has a distribution which is very similar to PZ. Now the point is, when you are starting at the training part of it, then QZ is not going to be very similar to PZ. There is a random chance that it may be, but in general it will not be. Now the question is, if that is the scenario, then can the only way we can modify Z to follow QZ which is equal to PZ is by making some modifications to this encoder, which is represented as a distribution model of Q of Z given X. Okay. Now if I want to change the distribution model over here, so then I will have to change the weights. So appropriately, the weights over here have to be identified based on what is the loss function or the performance of this discriminator. Now look at this fact. If these two numbers are coming from two well-known distributions from two distributions which are very apart, there is no confusion, then the accuracy or performance over here is going to be 100%. So the loss for this discriminator over here becomes 0. But then I don't want to make the loss for this discriminator 0, because if that happens, then these two are not very close. Now whenever these two are very close by, the discriminator loss will be maximum. So in the best possible case, the discriminator's accuracy will now be 50% accuracy. And that's the state which I actually want to achieve, that I want to achieve a state of 50% accuracy in this discriminator's performance. Now the question is that since I want to achieve 50% accuracy in the discriminator's performance, can there be a role of this encoder to be able to achieve that? Now the way we want to do that is by doing some sort of a message passing. So if the encoder has an indication of what is the state of the discriminator, what is its loss and performance conditions over here, then it should be able to do. So the way we do this message passing is by essentially sending the loss, also giving a component of the loss of this discriminator to this encoder. Now look at the way. So what the encoder wants to do is maximize the loss of the discriminator, or just exactly opposite of it. So if the discriminator over here has a gradient descent rule, which is it follows down the negative of its gradients and it wants to come down, then the encoder over here wants to modify itself such that it can rise the loss along opposite of that gradient. So now what that would mean is that a negative of the gradient function of this discriminator is something which should be used for updating this encoder itself. And that's the whole crux over here of how we can do this in order to make QZ very closely resemble PZ. So once you are able to do that, next comes the point of what will you achieve. Okay, so here you can see what essentially happens from it. Now on the left hand side, what you have is a plot of different point, and then the points are colored. So each point, essentially, if you look into it, there are 10 different colors. Now each color represents one particular digit in that MNIST. So what we were trying to do is that we were trying to train a Lenet kind model. It was not a Lenet, it's a simple autoencoder, the kind of autoencoder we did in the first week in order to classify and then encode your digits. So there was a very simple digit recognition engine which we had built up in the first week itself. So we are doing the same kind of a thing over here. Now here the whole job is that given you have this set of digits. You train this autoencoder in such a way such that the latent space Z starts behaving like it's drawn from a zero mean Gaussian distribution with a variance of I think plus minus 5 was the variance over here. Okay, so in that case you would see that it needs to follow this kind of a convex distribution. Now the point is, now that I have trained this whole network, if I can actually draw some random numbers from here, draw a random z, a z from this 2D distribution, then you pass it through this decoder, which is the block over here. So I have drawn that whole thing on the left was drawn from this PZ distribution, and I pass it over here through this decoder block. Then I'm supposed to get something which looks like a number. Now here, when I do that and I keep on varying, so I would see that it would keep on generating numbers which look like this. Now see, what I give as the input is just a 2D vector and nothing more than that. Giving a 2D vector on the input, I am able to get down an output image of size 32 cross 32. And they look very realistic, like handwritten digits over here. So this is what I'm able to do, and this was again following from the original concept of what we had done last week for a generative model, that I want to give a low dimensional space onto it, some very few numbers, and then from there I should be able to generate much high dimensional space or a well looking space of digits completely. So is that clear to everybody? So is that clear till this part? Okay. So if you get confused at any point, please don't wait for me to come back and give a breather and ask you, but yourself just type it in the chat box the moment you get lost of any track or a thread over here. Okay, because this is a bit grueling from now on. Now here, there are different ways of changing it. Now, if you look into this earlier case, see what I'm able to do is I can draw a random number from this kind of a distribution and feed it to the decoder, so I will get down some digits. But then I don't have a control of which kind of a digit I am generating. So say that I wanted to, we train a neural network over here, and this network with this adversarial autoencoding policy of mimicking somebody's handwriting, some very famous person's handwriting, maybe Shakespeare's handwriting, and now you want a particular text to be written in the same way as Shakespeare would have written with its handwriting. Now the issue is that you will not be able to really know that which random value is going to create which number, so or which alphabet or something. So now essentially what you will have to do is that you will have to get this whole collection of lot of random numbers, from there get down lot of digits coming down, and then put them through a classifier or something, and then exactly map it back over there. But then this is not going to look a very continuous process. Now instead of that, the point is, can we in some way do such a thing that if a random value comes from a certain distribution, then that will always lead to a certain type of a number. And that is something which we do by putting down an adversarial autoencoder with regularization inside over. So the whole concept of putting it with regularization is something where I give an extra meta variable over here, which will decide as to which part or which exact distribution is from where a certain class of random numbers are generated. So now on the right hand side, what you have is each color represents a particular class of digit over here, and this is my Z in 2D space. Now surprisingly, what is different is in the earlier case, you would have seen that it's a single Gaussian distribution with same variance along the x-axis and y-axis, and that is about plus minus 5, and you have your mean at 0. But here, if you look over here, what we are trying to do is that every single number has a very distant distribution, which looks like the petal of a flower. So this looks like a 10 petaled flower over here, and every single of them has a different kind of a distribution from where it is generated. Okay, now that I have this part, what this will enable me to do is that we will now be able to get down numbers which look um, as if it's drawn from a particular class. So if I'm drawing something, say from this purple class or from this green class or from this black class, then any random number drawn from here will all represent the same digit. So under a different stroking pattern. So it can be vertical, it can be horizontal, it can be bold, it can be thick, it can be narrow, any of them, but it will represent the same digit. So if it is 1, then it will always be 1. It can be a straight faced 1, it can be this kind of inclined 1 or this, or it can be a factor 1, it can be one which looks very closer to a 7 or something, but then they will all be 1s. Okay. Now what this will enable me to do essentially over here is that this whole thing now lets me create a model whereby I can choose exactly which number I want to generate, and that's the whole regularization principle coming into play, which is going to help us do this. So now how we end up doing that is you put this extra kind of a selector variable over here. Okay. So the job is that you put a particular class of numbers. Say I put all zeros over here. I get down all these meta variables coming, all of these latent variables or z coming over here. Okay. Now that I have all of these z's come over here, I take for say the number 0, I have one distribution. Say this is this blue. So every time I draw a sample from this blue and I get this one, I will also send a one hot encoding over here which says like which class of a number this belongs to, and this together goes into this discriminator over here, and the job of this discriminator is to say whether this was coming from this distribution or from anywhere else. So anywhere else is, so if say this number from here is coming from this distribution of red. So if this is 0, this is 1, this is 2, maybe this is 2. Then also it will say that okay, this is not from the distribution of this one. So that's what I essentially want to enforce over here by giving this class specific regularizer, which helps you in understanding that which distribution should you adhere to in order to get this one confused. Now what that would enable me to do is that there is an extra conditioning which I'm giving, and by this conditioning I'm able to condition that everything goes on to coming from a fixed kind of a distribution. It does not come from some random places in some way. So are we clear with that? Just think over it and then write down in the chat box if you guys are clear with this part. Please ask where you are confused. I need an acknowledgement which says that it's okay, it's clear. So I'm assuming that most people got it, and then you don't have a query on this part. So I will proceed to the next one. Okay. Now there are different ways of another few ways of doing it. So this was an example where the idea was that you don't exactly pull it up from only a Gaussian distribution as in earlier cases. So in the first case, we did see that it was a very isotropic Gaussian distribution where the variance along both the axes was the same. But here what we want to do is that we want to pull it out from a distribution which looks very different. So and this one is a Swiss roll distribution. So the whole point over here is that any random number which is getting drawn from a Swiss roll distribution is supposed to come from this kind of a Swiss roll pattern. So Swiss roll is something like your pastries, those roll pastries which you have in canteens. So it originated basically from the name of that. The Swiss patissiers used to roll their cakes with icing sugar inside over there, and as a result of it, that got this particular name of what is called as a Swiss roll. Now, if you have this kind of a Swiss roll distribution, then you can use this kind of a model in order to generate that and put a similar kind of a conditioning. So now what you are going to do is that in this earlier model, instead of putting a conditioning that it comes from a different kind of a distribution over here, you can slice a piece of that distribution as belonging to a particular class. Now from here, there is a advantage which you get, that you can have some sort of a proximal continuity generated. So you say that I start from this, and if I know what is the topological map, and if I traverse along this one, which is also what is called as a traversal along a geodesic contour, or to travel along a contour, and that's a geodesic traversal. So if you have a geodesic traversal, then through this geodesic traversal you will be able to generate all of these numbers over here. Okay, so this was another way of trying to solve this problem and actually getting to do this one. Now that's not all. There are also different ways in which you have something which is called as a supervised adversarial autoencoder. Now what happens within this supervised adversarial autoencoder is that this whole thing can help you actually decouple the content from style. So content essentially is what is the number which you are telling, and style for us is essentially the stroke pattern in which you are going to tell all of this. So what this means is that say I'm writing this number 0, or I'm writing the number 1 or something of that sort, then what I would like to do is that I would like to have the nature of my stroking pattern, or the handwritten digit patterns or everything looking very different from different person to different person. So it is something like the way I would write down some numbers and the way you would write down some numbers, they are very different to each other, and that is what is called as the style over here. The content is essentially which is the digit which I am writing, or which is the alphabet which I am writing over here. So the whole point within supervised adversarial learning is that you put in your digit over here, which is X, or some input, and you get your Z. Now the way we can decouple this content from style is if you get a Y, which over here essentially is something which is just conveying what is the content which you are doing, which is what is the digit. Say you are writing the digit 1, 2, 3, or whatsoever, and style is essentially how I am writing it down. Now the way this is different from the previous case of autoencoder with regularization is that over there I was giving this conditioning to the decoder, to this discriminator, whereas here I am giving this conditioning to the decoder, that which is the class of the digit I am actually mentioning over here. Okay. Now by way of doing this, what we are able to do is that, say I give a sample of handwriting of yours, okay, and I also tell which was the digit you were writing. Now this, since I am telling what is the content or which was the digit you were writing, so that is an information which is passing from here. Now the only thing this Z will have to start encoding is your style and nothing else. Okay. Now if I give your content, so now to this decoder what I can do is I can give the content, which is I can say like, okay, this is the ASCII value, or whatever is the class label of what you will have to generate, but you generate everything which is going to come from a particular kind of a style. Okay, then you would see that contrary to this earlier mechanism, say in the earlier case with regularization, what you had is you were able to generate numbers for a particular class, but you did not have control over how that would look. So I would pretty much assume that this, and this two are being written by the same person, because they're all on my right inclination. But then the point is that you cannot really ensure by looking at a random number that you will always be getting this one. So only after you get the output that now you will have to somehow ascertain that whether they look as if they are coming from a similar kind of a writing style, and then we will integrate all of them and work it out. Now the issue is that I don't want to do that. I want to rather specify a style, pick a some point on this distribution and say that every content which comes down, I want it rendered in this particular style. And that is possible when you have a conditioning which is like this over here in this kind of a supervised autoencoding mechanism. The reason it's called a supervised is because you have the class labels and everything coming over here. And if you did not have class labels, then this wouldn't have worked out. Okay, so now if you look over here is what is an example of what is possible through this one. So on the left hand side, what you see is all standard digits from different styles in MNIST. Okay, these were different stroking patterns in which it is written. And on the right hand side, what you see is the same kind of numbers which are generated, but they look like they are from Street View house number. So Street View house numbers is a data set of numbers of images of images of house number plates. So like in certain countries, I mean in our country also, in certain places you would see that houses have numbers. I mean in general all houses are allotted numbers, but we don't typically make an attempt to write down the number of our house outside the house. Now that's a very standard way of how to reach out a coordinate system. And any, I mean typically in India, for any municipal town or even rural areas, your administrative authorities do it. So you would see that your house's tax certificates and those challans would also be drawn down with a number called as a house number, and typically that's supposed to be part of the postal address, though we are not used to that and we don't do that, which makes the postal system really go cranky while finding it out. Now, say like my house has a house number 298 by 250, and then that is how it's associated as a unique one. Across all the other houses on the same street. Now here the concept was something like this, that Street View house number is going to have a different style and MNIST has a different style, but this content is basically what is the digit which is given over here. So here the reference was that this whole thing belongs to a different style. This thing, so in house number the first row is a different style, the second row is a different style, the third row is a different style. So each has a different style. Now if we pick up a particular style, say we were given this example of this 0 and that was the style key which was given. Now for every other number you will be able to generate on this sequence. So given this 0, I am able to generate what in this thing would look like a 1, 2, 3, 4, 5, 6 and then so on and so forth. For each of them this is what was done. So the first column was basically the key which was given to identify the style, and then all the subsequent numbers were what are generated based on this particular style coming from that manifold. Now, looking at this example, what do you think can be a very important practical implication of this one? How can we practically utilize this? How do you think we can practically utilize this kind of a system where uh, you can get to choose a style, and given a content or a number over here, you will be able to generate uh, that number on that style. So essentially I give you a reference style of 0 and I tell you that generate what will 1 look in the same kind of a style. Then what is an advantage? What can you build on a product with this kind of a system coming into play? Yes, this was to everybody. When somebody needs to make an attempt, or essentially each of you need to make an attempt to write down something on the chat. The chat can pop up on by clicking on the messaging icon on the top right corner of your browser. So is the class actually there, or people are just logged on and then you have gone back to sleep? So people in the class, if you are not confused and if you have gone through till this part, then can you please tell what can be a product which can be built from this? That now that you can generate numbers from a different style. Address recognition on postcards, as everyone. That is when you are looking at a classification. But here I am telling that I give you a style of a number, reference style, and some other number which is not present in that style. So I give you a 0 from this signboard over here in this first top row and first column. Okay, and then I say generate how will 4 look like, and you are able to generate this one. But the network has not seen how a 4 looks like over here. So what can you do with this? Mannan says translation. I did not get your point. Maybe you can unmute your mic and speak out as to what you mean by translation. Whale has a very dangerous thing, fake news generator. So I will ask Mannan first and then I will come to Whale. So Mannan, please unmute your mic and say what is a translation. Mannan, not able to hear you if you are speaking. You said translation to translate to other languages. Okay. As in, how do you want to translate to another language? Using one word as the style to another language. Yes, yes. Now, yeah, you actually have generator models within natural language models as well. So what you can do is that you have some text written in one particular language, you can generate the text in another language. But what we are going to say over here is that creating a sentence based on that. Yes, here it is more of like I give you a reference of how typically I write or I speak. Then any other standard way of writing or speaking which you have, can you use that and then generate down the same way as like how I would be speaking or writing. Yes, that is one. But then you are very much tuned on to looking at languages, and then in part of this class what I wanted to emphasize is that really grow beyond that. I mean, this is a closed shell in which you are always thinking. So either you are thinking only in terms of languages or you are thinking only in terms of vision. Now the objective is like break this shell and then come outside it and then start thinking. So start thinking more of in context of what is given to you. So here, like say if I'm giving you images and now I say this, then think about what this can be used for doing more. So I'll come to Whale and ask him. So what is your point that you wrote down? It can be used as a fake news generator. So what will it be?
So then there's a document which you want to fake, which was written by a person. So you can basically take some inputs from the image which is already there, and then using the same styles which are, I mean, we can generate a different document which might seem like it was written by the same person.
Yeah, yeah. So that also goes in line with what Abhijit was writing over here, that writing a whole text in any font. Now you might not want to do this in a very trivial way of any font, but you want to just duplicate somebody else's handwriting. And then that's essentially what happens in things like deepfakes. You might have heard of these things called as deepfakes. Now in deepfakes, what they do is that there is one actor who is speaking something, and then you take a reference of another person's image. So there was something which was spoken by some Hollywood actor somewhere, but then you took down. So there was this whole controversy created that that dialogue was spoken down by the American President Donald Trump. And what they did is they took that person's image and they put it. And I know that in the wake of a few of these insurgencies we had before the COVID-19 crisis in India, there were a lot of deepfakes which were circulating about Indian political leaders as well. And a lot of these deepfakes are what get generated. I mean, in fact, deepfakes are generated through the same kind of a concept. Now here, what you are going to do is essentially you are faking. So things were made for a more purposeful way, a better way of how you get it realized and how you use it. And one of the primary things for this, and then we had some work we were doing at a point of time, was that say you have images where certain parts are patched off and then it's gone. You know what should be there as a content wise, but the whole thing is distorted. So there was an image of say these house number plates, but then in between something got chipped off. Physically it was chipped off, and then you don't know how it was written over them, and then you want to get it back onto the old format. So this can be something, you know that somebody's house number is 345 and this 4 was not present, but you had the reference of style from 3 and 5. Now you give that reference over here, the style from 3 and 5 comes over there, and this 4 is not present. So now essentially what you can do is that you say that the number was 4, which is the context which you are passing down over there, which comes from here, that you say that this y is basically the context vector which is 4. From 3 and 5 you got your style vector, and now that you have that, you will be able to represent this number 4. So this can be a very good way of doing something which is called as an image in painting, or a way of what we have in image restoration processes, that some part of the image is degraded for some physical processes and I would like to restore them. So this is what you can achieve over here. So this was the actual reason of why these kind of things were created, but then there are always people who would find a misuse for every single thing which is done for the good part, and then the misuse thing was that you got a deep fake generated. Now similarly you have these apps on Facebook where you have aging and everything done. So how will you look like when you are 50 years old or 60 years old? So essentially, there the queue of somebody on that particular age is taken down as the style, and your face is given down as the content, which is Y over here. So there will be a derived content from your face and given down, and then you get this matching coming over here. So this is how essentially any of these faking mechanisms keep on working. Okay. So next I will come into how you actually model these loss functions and what happens within that discriminator over there. But yeah, so let's get into this. Now the whole point was that we were trying to model something which is called as the control plane of the problem. Now, what I said in the control plane of the problem was that you have some of these mechanisms of loss function minimization or actually training your model, which is called as say maximum likelihood estimator or mean square error. And then as we went on going, we came to a point of what is called as a perception loss. And then this perception loss is a primary thing which we want to model over here. Now, how we get it done is the primary point. Now, one way which I was showing you as an example from the early on weeks on understanding distortion versus perception loss was that you give say this kind of a sketch, and this to you is now going to be the content in some way. Now that you know that there can be styles and content, and then if there is a very improper style transfer, then you see that the house will look like this. But if you had a proper style transfer, then this is what it would look like. So I give a lot of photographs of actual houses and then say like this is the content and please render me according to this type. In that case, my generator model will be able to do that. Now the moment this happens, you would see that this image looks very close to that of an actual photograph of a house, and that's why you have a very low perception loss. But then there is a lot of distortion on a pixel by pixel measure, and that's why you will have a very high mean square error. And that was the whole point. And how you minimize that is that you bring in this extra kind of a network called as the discriminator network, and this was that part which we are seeing in the bottom of the earlier figures. And the job of the discriminator network is that here we don't have a latent variable distribution in any way, but here we have the whole image. So either I'm giving it this generated image or I'm giving it an original image, and then I'm asking this discriminator that you say whether which one is real and which one is fake. So initially, if this style transfer is not properly made and the generated image is not very good, then you would see that this generated image looks very different from the real photograph, and that's how the discriminator neural network can very easily say that no, this is generated, this is a fake one, and this is not a real photograph. Now that defeats my purpose, but the point is that this generator or this sketch2 photo CNN somehow has to have an indication of what is the performance of this discriminator, such that it can tell that the generated images are very close to the real looking photograph. And that's what we want to achieve over here. Now, in order to do that, how we get the mechanism is something like this. That say I have a database of lot of real images. And now what I'm doing is, whenever I give this real image to the discriminator, it's able to tell me that this is real image. That's one part. That is gone. That's very good. Now what I would do on the other side is that I would draw something from a random distribution and give it to a decoder, and that decoder is going to generate something and then give it to the discriminator. Now if say whatever is generated from the decoder looks very different from a real image, then the discriminator can very easily say, now that defeats my purpose. So what I would do initially is that I find out what is the loss function, and then this can be a quantitative number. So essentially whether it's coming from here or there, that's a ground truth which you know, which you can use for training your discriminator over here, which trains it using the binary cross entropy loss. So now what I do is I update my discriminator in order to minimize the loss. So that will be a gradient descent mechanism. So I'm going to pass down the gradient of that discriminator loss or nabla JD. Good. This part gets done. Next, what I do is my decoder has to start confusing itself. So decoder has to start confusing the discriminator. Now what that would mean is that the decoder would modify itself such that there is a gradient ascent in the discriminator, or the loss keeps on maximizing. Okay, so now you can do that by essentially creating a new kind of a loss function which is called as adversarial loss. And in the best case, if the situation persists something like this, that your discriminator loss is limited up to 1, then 1 minus discriminator loss is what is going to give you your adversarial loss. Now you have your adversarial loss over here, which has to be passed through the decoder, and you have that one passing through the decoder. So this becomes minus nabla JD. Are we clear with this part? So if this whole thing has to do, so how this minus nabla JD comes is because you have nabla J of adversary, and this one under derivative will not exist, so that becomes 0, and then you will have minus nabla JD, or the derivative of JD. So this is what goes through, and this essentially is trying to do a gradient ascent, because that is exactly opposite to what was gradient descent mechanism over here. And then you update using the standard backpropagation rules itself. Now, this is not the only way you can do that. Apparently, it turns out that you can also use something which is called as a feature cosine similarity loss. So the idea is that you either take this thing which is generated, an image which is generated from the decoder, which is fed from a random number, or you take a real image and then feed it through some sort of a pre-trained CNN. Now this pre-trained CNN can be something like a VGGNet, AlexNet, or any of them. You just dump out or delete the final classification layers. Now that you delete the final classification layers, you are left only with uh, the features available over there. So you will have a feature which corresponds to this. You will have a feature which corresponds to this. Okay, so this feature is what is known as y hat. This feature is what is known as y. And you take a cosine similarity between these, which is basically the cosine distance loss between these two features over there. And then that's the only thing which you have to do. So now you can train by basically doing a mechanism in which you want to minimize this loss itself. Okay, so there is no update on this pre-trained CNN. The update will only be through the decoder over here. Okay, good. Now next is we come down to something which is called as a Turing loss, and this is a very interesting one. Okay, so the whole part of a Turing loss is to do something like this, that I take in some random numbers over here, and I'm able to generate this uh, image over here, which is a fake image. I take in a corresponding real image over here. Now I basically use a block which is called as a shuffler, and the role of this block is that you are in the earlier cases, what you are doing is you are either showing the discriminator only this or only this. You are not showing both of them together. Here, this is more of like trying to solve a spot the difference puzzle. So in a spot the difference puzzle, what do? You remember a spot the difference puzzle in newspapers which comes down. So you are given a pair of images, and then you will have to find out what is the difference between these pair of images over here. So here also it's the same kind of a problem. Now you are given this pair of images. You will be given one real and one fake, but we are going to basically shuffle the order of which one is real and which one is fake. Now, the moment I shuffle this order of which one is real and which one is fake, your discriminator now is posed with a very interesting problem. So the discriminator now gets posed with the concept of trying to solve something which is called as a Turing test. And this is something which we had discussed in the earlier classes. A Turing test is essentially something where you are asking the machine to tell whether the thing over here, or whatever you are seeing, is real or fake. So that was Alan Turing's basic definition of creating intelligent machines, and here we want a neural network to do, but then we make it a bit tough. So if we always give the real first and then the fake, then it can always say that the first stream is always coming to be real and the second stream is always coming to be fake. It does not really learn to articulate the differences between a real and a fake, the actual subtle visual differences. Now here we are trying to do this whole part by solving something where you have a pair of real fake or fake real. So you essentially shuffle the order between these coming the back and forth, and then you pass it through this Turing test. And the job of this Turing test is to basically predict whether the first channel was real and second channel is fake, or vice versa, and nothing other than that. Okay, so now your update mechanism will be, you will try to make this Turing test better and better possible, so that will follow a gradient descent, whereas this decoder has to be made to go to a point where it will confuse this Turing test to the maximum. So this will follow a gradient ascent, and that's why the update will be with minus nabla JD. So are we clear till this part? Are we clear till this part of the different loss functions? Can you just type and say? Okay, great. So let me continue from here. So now what we are trying to do is get into something which is called as a generative adversarial network. So the whole part over here is to do something like this, that I take a random number, I generate some image, which is essentially a fake image. I also take a matching image from a real database, and then I feed these two to a classifier. Now, the job of this classifier is to say whether the image which is generated as fake and the one which is generated from real belongs to the same class or not. So essentially, if I want to generate fakes of dogs, then the job of the classifier is to say if whatever is generated looks like a dog or it does not look like a dog, and nothing more. It's not going to comment on whether it's real or fake. Okay. Next, the other job is that you will take some other images which will be of different classes, and typically this is taken from a standard database of some other classes of images, and you give it to the classifier. Okay. Now, through this whole mechanism, the classifier is learning to discriminate between their dogs or some other category, as in this example. And then this is just a classification problem which this is solving. Okay. Now, there will be a loss function which will come down, and you will want the classifier to become better and better possible. So you have a gradient descent carried down with the classifier loss. Similarly, you would want your generator to also become as good as possible or as close as realistic to generating actual images of dogs. And that's why you will be updating your generator also with the same kind of a loss. So this is not somewhere where your generator wants to confuse the classifier. Your generator actually wants to aid the classifier in telling that these are dogs and these are not dogs, and so you, if the classifier has a better performance, high performance and a low error, then you also say the generator that your error is also low. Otherwise, if you are generating something which was not looking like a real dog, then anyways the classifier would have been making mistakes over there. Okay. Now, what we bring in is also a discriminator whose task is to say whether whatever is generated as a dog looks very close to a real looking dog or not. Now here, the job of the discriminator is to is to become as good and as possible in order to discriminate between real and fake dogs. But then you want to tell your generator that if your discriminator is becoming powerful to discriminate between these two, that essentially means that you are not generating fakes which look very realistic. So now you need to start generating fakes which look very realistic, and that can only be done if the generator has a gradient ascent on the loss of the discriminator. So this together sums up what happens within a generative adversarial network, or what is very popularly known as GAN, and forms, like, ask anyone about what is adversarial and then they would speak out that about GANs. Now the point is GAN is not all of that, and that's the reason why we started with understanding adversarial autoencoders at the start of it, and then so that we don't get confused with GANs. But GANs are also some way of achieving this. So GAN is one part of doing a generative model. You can also have adversarial autoencoders. You can have, similarly, you can have deep leaf nets and then Boltzmann machines also to generate as well. Now let's come on to this. What happens with the loss functions and as you are learning? So what you would see is that the classifier loss, as you are training over epochs, will keep on decreasing. Okay, and that's for sure that has to happen because I'm aiding both of them to achieve the same thing. Now, you would see that the discriminator loss over a period of time is actually increasing, and it will come to a point where it will saturate, and this will saturate. So if your discriminator loss is limited between 0 to 1, and at a 50% error it will have a loss of 0.5, then this will saturate at 0.5. So we don't look at the loss because binding loss is a big problem. You don't typically know what is the upper bound and the lower bound for losses, but we have a very good understanding about what are the upper bound and lower bound on accuracy. So if you look at the accuracy of the discriminator, then you would see that this accuracy of the discriminator would be limited at 50%, and that is what would happen when uh, this kind of a model is getting trained adversarially. Now the reason for that is that the moment you are able to generate your fakes which look very realistic, then half of the times it will confuse and then say a fake to be real, and half of the times it will say a real to be fake, because it's essentially taking a chance uh, phenomena distribution over there and nothing more. So that's the reason why your JD or the discriminator loss over here initially will be in a dynamic fluctuating state, and then it would come to a point and then converge at 50% position. So are we clear to this, clear till this part? Okay. So now let's get into what is the difference between a generative adversarial network and an adversarial autoencoder, because these were two different things which we have learned till now. Now the primary difference which comes in is that in a generative adversarial network you have a classifier over here which is going to do this state classifications based on the complete image, and then you have a discriminator which also does whether it's a real versus fake by looking at the complete image. Now if you compare that with an adversarial autoencoder, your discriminator does not work on the complete image but it works on the latent space. So this is the first part. The next thing which comes down is that your encoder decoder anyways is present over there. Now the total number of network components does not really get reduced anyways, because say the generator which takes from a lower dimensional latent space onto a complete space of the image, here you have similarly a decoder which takes in from a lower dimensional latent space to a complete space of the image. The discriminator is something which is different over here, because here the discriminator input is of much lower dimension, whereas here the discriminator input is also of a higher dimension. However, the classifier component over here, the number of neurons and whatever you have, is typically of the same order as the model complexity of the encoder itself over here, because this is going to take in a whole image. The classifier takes a whole image and bring it down to a low dimensional space. Here it's a classification space, but here it's going to be an encoder space. Now, this image is typically what sums up on this particular slide as to what is the fundamental difference between a generative adversarial network and an adversarial autoencoder, and that's what we want to really emphasize. So the loss functions are also very different. The only common binder over here is that you will have a discriminator, and the job for any kind of an adversarial learning, so there is something called as an adversarial attack, and there is something which is called as learning in the presence of an adversarial attack. So when we say something like an adversarial learning for generative modeling, then it's typically, it refers to the point of learning of the blocks in the presence of an adversarial attack. The adversarial attack is what is being heralded by this encoder in case of an adversarial autoencoder and by the generator in case of a GAN. Now it's attacking the discriminator, because what it's trying to do is it's trying to modify itself such that it can fool the discriminator. So the discriminator is the one which is getting attacked, and the adversary which is attacking it is the generator. So similarly for an adversarial autoencoder, the discriminator is getting attacked and the encoder is modifying itself to attack the discriminator. But then the discriminator is also learning. The discriminator is not a static block. The discriminator is also trying to update itself in order to fend off this attack. And that's the reason why you would see that in the initial part, you would have this kind of a dynamics in the discriminator loss. So this is where the discriminator is trying to fend off the attack, and so this is the point where the discriminator, because this is loss, so this is where the discriminator is performing really good, and that's because the generator has not been able to attack it very good. But then over the time, as the generator's loss, as the generator becomes more and more powerful in being able to attack the discriminator, so the discriminator loss keeps on going. Now look at this part. The moment the discriminator loss keeps on going up and up, the adversarial loss, which backpropagates through the discriminator, is going to go low and low. It will keep on reducing. So that's how the generator knows that it has been able to very successfully attack the discriminator over here. So that's the whole thing, and the beauty of how this kind of learning in the presence of adversarial attacks happen. Now, to go more through it, I typically recommend this particular paper by Carl Distortion, and then this is on tutorial on variational autoencoders. Now, a lot of things which I have done till now from the previous weeks itself are based on this particular paper. So this will help you really understand. You can also get into this particular archive preprint available. I think now it's a full paper which is on adversarial autoencoders, and it's a very good tutorial style written. So all the examples which I was giving over here are based on this particular paper. So that's where we come to an end with the adversarial learning. So we'll just take a 5 minutes break. We've been on this call for quite some time, and then so don't leave. I'm not blocking out the chat room. Okay, everybody. So we are back, and now we will start with the part on some of these application areas which I'm going to show you. So the whole point is that by now you have some idea about how you can train an adversarial, train a network adversarial, and how you can do some sort of a generative model with that. But now I'm going to get into like what are some use cases and where can you use it? What's a practical scenario for this one? Okay, so now one fundamental point is to look into doing something which is called as a perception loss. Okay, and the whole point of perception loss is as we had on one of these earlier classes was you don't know exactly, you know what's a mathematically tractable form of say mean square error loss or something, but then we don't know what is a mathematically tractable form of a perception loss, which is whether an image looks very realistic or not. So this is what we call as a perception loss. So if I throw you this question over here, so you can read through it. So essentially what you have is a pair of images, and these images, so one on this pair is a real image, the other one is which is a generated image. So these images are what are called as intravascular ultrasound. So this is a particular kind of a medical imaging modality in which, so they are ultrasound images for the general purpose understanding. So I'll get into how these are generated and everything. And the whole point of generating these ultrasound images was we wanted to have something where you don't have a lot of data available for training purposes. So training as in not just a machine learning training, but it can even be for human capacity building and training human resources itself. So we don't have a lot of images available in order to train people, and then we wanted to use this in order to do. So you give an anatomy and then can it generate a medical image corresponding to that particular anatomy. That was the primary goal of this particular problem over here. So now what I'm going to ask you is, can you discriminate between which one is real versus which one is fake? So just look at them. I would still be hopeful that the video quality is decent enough for you to understand. And now can you write down, so who believes that the left one is real? So you can just write on the chat box if you believe that the left one is real, or whichever is real, you can just write on the chat box. And then which one you think is a fake or a generated one, you can write. So whether it's left or right, just write left or right, and I understand from there. Okay, I got one response. Okay. Yeah, let's get some responses from others as well. Rishikesh first wrote down that right is real, then he right says left is real. Whale is not able to see the video properly. Uh, I should have shared these slides before starting. Next day onwards, I will share the slides ahead of it so that I can read out the slide number and you can have a detailed one on your side as well. Okay, so if I just do a gross summary of how many said that this is real and that is fake, then it's almost at a 50-50 level. Half of the people said that left is real and half of them said that right is real. And then that brings me to the point, then we have done a very good job. So I know that people who have done this one have done a very good job because we had a similar kind of a response coming from standard ultrasound practitioners or radiologists who do this as a day in and out job. So let's get into, but that is not the point of like how we have been, how good have we been able to do successfully full experts. But the primary point over here is to see like uh, how did we do this whole job where we are able to generate images which look very realistic itself. Okay, so the whole part of this story, how I tell is, and then this story has a deep rooted thing. So this is something which I had started somewhere in 2010, and it took 8 years and then even more. I mean, we now in 2020 we have the recent most paper which is on 2D to 3D mapping for generating ultrasound volumes, and that is where we are somewhere closer to the end goal of what I was dreaming in 2010. So we'll have a subsequent lecture on that one. Let me try to figure out if I can get the first author of that paper, Anand, to come on the on this meeting room, and then he can present to you exactly the whole journey of how we did a lot of tensor modeling in order to get this one done. Okay, but then this was based on, I don't know whether you know these guys. Some of you might have seen his face, Francis. He graduated last year. He was the best thesis awardee for these works which he was doing. So this was like 2 years of a work. So he worked on his masters and so for his bachelor's thesis, for the BTech thesis as well as the MTech thesis, he was on a dual degree program, and this was an outcome of that. So this is the first part of that paper, which was from 2018. We had subsequent ones on image compression using these kind of things. So I will come into use cases more and more, but this is about how you created one engine and then you could go down to the next one. And I also made a statement of acknowledging our machines as well, because if not for these two real workhorse machines at that point of time when we were not yet a 1 petaflop tensor system, it would have been very hard to prove out these ones. So now the primary thing which we did is we basically, how I put the story is that we have been able to use deep learning in order to answer some very fundamental imaging physics related problems. And this is where the point goes down to that we can use data and we can use our current learning methodologies in order to start describing how physics of physical processes work, how these physical processes are actually get to work and how they can be used and made more and more powerful. So this is about discovering more things from data, and that's the real power of why you would want to do something with deep learning at any point of time. Now, if you have not seen an ultrasound machine, then this is the one which you see on the left hand side is a very typical ultrasound machine. So sometimes I think even for your admissions for IIT, you had to go to a doctor and get an ultrasound scan of the abdomen or something done. So they had used a machine like this, and then this is what comes out. And on the right hand side, what you see is basically an image of the liver when it is imaged with an ultrasound. Now, for non-experts, it's very hard to say what is this organ and everything. I've been working on ultrasounds for quite long. I had my whole PhD on ultrasound. So looking at that image and telling you exactly what organ it is something which I've been trained over the years to do it. Now here let's get into what is my primary point of discussing all of this. Now typically in this machine what it has is that you have something called as a transducer. These are basically transducers are sensors and actuators combined together. So you will have one single element of a piezoelectric crystal which can vibrate. So if you give it some electrical voltage, it will vibrate and create a mechanical wave which will pass through tissue. Similarly, if there is a vibration which comes to this one and it's vibrating, then it can also produce an electrical signal for you. And that's the whole point of why these ultrasound transducers are used over here. So what happens is that if I start a vibration over here, it's going to propagate in free space, and this follows down something called as the Huygens principle. Now, if it strikes on a hard media, it will reflect. If it does not, then there is no reflection coming back. But then what I do is I set this wave going. So it's like just throw a stone on a puddle of water and you will see this wave expand over there. So similarly here what we do is we set in a vibration and then stop this one. We don't vibrate it anymore, so that this wave is actually propagating over here. Now that this wave is propagating, it's going to strike somewhere and then reflect. But here like there is nothing to strike back. But what we do is now that this is not vibrating, so we switch it on over to the receiver mode. So in a receiver mode, it is supposed to sense back all the signals, and if there was a vibration which comes back to it, then this is going to give you an electrical equivalent signal over there. So now that signal is read out over here and is displayed. So we'll get into each of these parts, but as of now, just see that it is getting displayed over here. Now you would see some signals values, but these are not very strong signals, and this is inherently what is called as noise in any kind of a physical system. So this is typically Boltzmann distributed noise, and then after sampling it becomes quasi distributed, and you see that noise coming over here. Now if I set the next transducer running, so that is also going to emit something, and this does not hit a hard surface. Now I set the next one. Now this one, if you see, this will hit a hard surface over there, and from there you will get down some reflections back. And now if you get this image, because this is sound which is traveling, so it has a fixed amount of time it will take to travel from here to here and from there back to here. So I can use that indication of how far off, how much time has it taken to come back, as some measure of indicating from where did it come back. So using time, I can extrapolate that and go back to my point in space from where my reflection has happened. Now similarly, I keep on doing this back and forth, and then every time it strikes back, it's going to have. So I don't have that all of those animations being shown, which is quite intuitive for you to understand that it is going to get reflected, and based on that reflection, I'm able to generate this image. Now you can read more details about it in these two particular papers, and in fact the first paper, which is on signal processing overview of ultrasound imaging systems, it's a white paper from Texas Instruments. It's a very well written and explained informative paper for understanding what ultrasound imaging is and how the whole process works. Okay. Now we are looking at a point where I would like to simulate ultrasound. So the whole concept is that you can either take a real ultrasound machine and get an actual human being and take images from them, or the other option is that you give a drawing, which is what is called as a phantom, to some sort of a computer generated numerical simulator, and this can solve all of these wave propagation equations from where it will get reflected and how it will look like. Now that you are able to do all of this, this will help you get this kind of an image which is created, and this is what is called as a simulated image. So here what we are looking at is that given the image of a fetus, you would basically be able to simulate and then do this. Now Field 2 is one of those very early programs, and till date it's a very popular program, computer program available for simulating ultrasound. But then this always does not solve your problem, and the bigger part is that by virtue of the fact that it's a numerical simulator, so the whole wave equation gets solved in a partial differential equation kind of a way, and then you will have these numeric solutions being solved for every single piece over here. So this is the PDE on a these kind of small gridded models which are getting solved. So it's a huge amount of computations. Now, now that it is a huge amount of computation which goes in over here, the challenge which is that it's going to be very slow. So typically, in order to simulate this kind of a image of say about 60 by 80 pixels, it takes almost a time of about a couple of hours on very standard Xeon grade system. So if you're looking at your laptop in order to run this program and simulate this image, it's going to take you about a day. You have different parts of the solver being solved. So there is an example on their website which is a partially solved out example. So you have all the pre-calculations done, and what you do over there is you basically run to generate the output over there. Intermediaries are calculated, but then you give a new phantom, you will have to calculate each and every step over there. So that is going to take a lot of time. Now, on the other side of it, we had these kind of options called as pseudo B-mode simulators, and this is from one of the works which I had done earlier, and this makes use of standard signal processing mechanisms of simulating them. So you know exactly what are point squared functions of speckles, and then you can use them and in order to do all of this stuff. But then this is a much faster method. The only issue comes down is that this is not a very reliable method. Okay. So how this method works out is pretty standard. So you take in a phantom, which is essentially defined that these are different kinds of tissues and these are the speed of sound available for each of them. And then you add some noise onto it, and this noise is going to be basically, your tissue is not a homogeneous structure. So tissue is made out of cells, extracellular matrix and all of this. So cells will be made out of nucleus and cytoplasm, and everybody has a different acoustic density. So essentially, if there is a wave which is propagating and the cytoplasm is a very acoustically not so dense structure, it hits upon a nucleus and then it will reflect back. And because it's going to reflect back from this strong structure, so you will see that there is a some sort of a speckle kind of granular patterns which are created. Now that is what happens. So this whole thing is mimicked by putting in a random location over here. You get down something which is called as a tissue ecogeneity map. Now on this, so when these waves propagate, you did see on the image that the wave propagates in this direction vertically, but it will also be spanning along this one. So it's not just that it's a point beam which is propagating. So there is a span in the x direction and y direction. X is the direction along which it is propagating, y is opposing direction. So these hx and hy are what are called as point spread functions. Now what we typically do is that these are also related to the frequency of ultrasound and some other factors itself. So hy is what is not related because it's a sinusoidal wave. So sinusoidal wave is going to be like this. So essentially it's dilating in this direction. So the whole sine wave, alternating sine wave kind of thing is what propagates along x. But you don't have that alternation along the y. In the y you basically have a spread happening. It will gradually keep on spreading. So it's not so difficult to understand. That same stone throwing on a puddle of water, you have seen that whole thing happen. Okay. Now here the point is that what we get back is what is called as the reflected wave, and this one is also a sinusoid. So you need to do an amplitude demodulation on top of it, which typically is a transformation called as a Hilbert transform. We take that, you have an amplitude demodulation, so you get your brightness factor or the intensity, and this is what leads to creation of this image. Great. Now that that is done, typically if you give this kind of a digital phantom for the artery on which we are trying to simulate. So this artery is basically the blood carrying vessel in your body, and we put a probe inside that. So imagine that this is a probe and this is my artery. So this probe goes inside my artery, and so if I do it like this, my probe goes inside my artery and this keeps on rotating itself. So this head of my pen, this part is where you have a transducer, one small probe of ultrasound, and this is rotating. Now this whole thing rotating is going to get me these waves coming back to me, and I will be able to get down a 360-degree coverage, and that's how I get down this. The point is that whatever you get in simulation looks very different from what it should be in real life. In real, for this particular artery is an image which looks like this on the right hand side, and the simulated one from the previous method is what you see in the middle. Now there has to be a mechanism to bridge this disparity, was the problem at hand. So we went back onto the challenge question over here, and then started looking into how can we actually bridge this whole thing. So one point we noticed is that there are a lot of these convolution kernels which we are using, and maybe these convolution kernels are not descriptive enough that they can help me in solving the problem. So now the point is that can I have a way in which I can learn these convolution kernels, and if I am able to do that, then I shall be able to solve this problem in a very decent way. So that's where we got into this whole mechanism. So one thing which you can have is you get into your standard CNN model. So instead of having one single convolution kernel, now we say that you have multiple convolution kernels, and these are all of these WIs. Okay. So instead of there being only one single point of a well-determined and a deterministic HX and HY convolution kernels, I will now have a set of those, and these are what are called as WIs, and they get me a set of outputs over here, which is called as Y. So this is every single of those intermediate outputs. Now I put it through some sort of a non-linearity, and then I have a combining kernel, and this is say something similar to that Hilbert transform which you had in the earlier function, and you will be getting down an output image which looks like this, and now you can do all of your mean square error minimization in order to do this. The issue is that you will need a lot of training samples in order to do. So which means that for every of these standard reference original images, standard reference whatever is simulated out, I will need a set of original images and a set of phantoms from where I can do. Now, if I look at this one from an ImageNet kind of a standpoint, or even for your MNIST where you had 60,000 images, getting that scale of images over here is really challenging, and that's where we are stuck. So we need to figure out some alternate way of doing that. Now that's where we had one of these kind of approaches, which was from a CVPR 2017 best paper winning submission, where the point was that you learn the models in the presence of a discriminator which is now adversarially attacked. So this refiner network which you see over here, the concept was that given a synthetic one, it should look, it should modify that and degrade it so that it looks very close as possible to this realistic image over here. Now, I'm not going to go through much details in the paper because you can read it through, and it's a very self-explanatory, and this is a part of Apple's product on retinal tracking as of today. So you have it on iPads and iPhones where you can open it up by staring at it, and then also if your gaze moves out, then it senses it from the camera is always on, and the device locks itself. So how they could get this gaze tracker and everything is that story which is over here. In fact, the CVPR talk is recorded. So what I typically suggest all of you is go and listen to the talk itself. It's a CVPR best paper talk, and then it's on YouTube, so you can get down access to the talk, and that will help you in understanding what was the rationale. But coming to this, like what we wanted to do for this adversarial transformation was something like this, that you have this phantom, you generate some sort of a model, and through the generator, and now you try to minimize the mean square error loss, and this is so that there is minimum geometric distortion which happens between them. And then you bring in a discriminator over here, whose job is to find out which is real versus simulated, and then while you are updating the discriminator, you also start updating the generator in order so that the generator does a gradient ascent on the discriminator loss. And that's the adversarial way of attacking the discriminator, which we had just studied about in the start of the class. Now, if you do this, you will be able to generate some images which look like the one in the right hand side. But there are still problems. The problem is that there are these kind of cross hatch kind of marks you would see over here where I'm hovering my mouse pointer. So these kind of hatch marks is what is not present in a realistic case, and you need to get rid of that. Plus the speckles are not very realistic over here. It generates something which is degraded like an ultrasound but is not actually that informative as an ultrasound. So now the issue which we saw over there was that there is a nonlinearity in sampling in space. So essentially what happens is if your ultrasound transducers are arranged like this so that they are radially emitting and sensing, what this would mean is that as you are far off from your center point of the probe, your radial sampling also keeps on becoming bigger and bigger. So now your speckles start smearing and spreading apart over there. Now this is what is a problem, because say for any kind of an convolutional network which has convolution, now convolution being a space invariant pattern, will always have the same kind of a degradation across the whole space. But here you see that there is a spatially varying PSF which comes over here. So we have to figure out a way of how to model a spatially varying PSF. Now, one way you can do is you take a fully connected neural network and do through that. But then that is not always a clear answer to it, because uh, if you look into the other side of it, which is the PSF is not actually that spatially varying. It may have happened over here. Essentially, what is the issue is that it is non-uniform in Cartesian space, but then it is uniform in the propagation in polar space. So what that would mean is that the PSF, if you are modeling in polar space, it would work out uniform. So now your neural network cannot have convolutions defined in Cartesian space, but they need to have convolutions in polar space. Now that brings me to a very new kind of a neural network formulation that I will want you to design a CNN which is in polar space. So that needs to be something like a polar CNN, PCNN. But that is not a standard mechanism. So what we found out is a much easier way of solving this. So what you can do is you can take a digital phantom. You can actually do a polar conversion of that one. Now in polar domain, what you get down is still a 2D matrix over there, but this is uniform in polar domain, so my PSF and everything, my convolutions can work. Now you generate a pseudo B mode, which is this approximate noisy model, and then you pass it through a stage 1 generator whose job is essentially to break this problem. So a PSF has, speckle has a height and a width. So what I'm doing is first I'm trying to model what is the height of the speckle, next I will be trying to model what is the width of the speckle. So this first generator does this modeling of the height of the speckle. Okay. So this is trained again adversarially by comparing it with the real image itself in the polar domain. Next, what you do is you freeze this generator's output and you take it through another stage 2 generator where now you are going to model the PSF. Now you can pretty much see that the size of the tensors over here, when you are trying to model the height of the speckle, you just have 64 cross 64 size tensor in polar domain. Whereas now that you are going to model the PSF of speckle, here you have a wider tensor of 256 cross 456. And this is again adversarially trained by comparing it with the full resolution real image in polar domain. And by way of doing this adversarial learning, we are able to get this whole network now created, which can generate images which look very realistic, and then they can pretty much be confused. Now, we are short on time, so I will not be quizzing you on this part. You can take the quiz on your side offline and we can discuss it again in tomorrow's class. And this has helped us in getting very realistic looking images, and this is a canvas of this one. So essentially I had the paper reference in the earlier slide, and you can read through the paper and go through more detailed images, zoom them up in and look into high quality images as well. Now, when we looked into a quantitative mechanism, we did find out that the speckle distributions are also very realistic. So there was a intra-tissue, which is essentially for the same kind of a tissue in original versus the simulated one, how much is the J's divergence, which is statistical similarity between them, and then the closer it comes to 0, the better it is. Then we also looked into inter-tissue dissimilarity, which is whatever is the contrast between two different kinds of tissues in a real, whether that same kind of a contrast is visible in the simulated one or not, and you can pretty much see that they are very close to each other in terms of the inter-tissue contrast as well. So this is where I will stop with the first use case. Tomorrow we are going to get back and discuss on another use case so if it is feasible to connect down, then tomorrow we will be discussing on how we extended this model from 2D to 3D, and that's an interesting tensor algebra problem. It does not have a lot of learning, but then it has something interesting on how you can now architect new models of neural networks itself and train them on lower dimensional spaces and carry them forward on higher dimensional spaces. But eventually after that we will come on to another use case of using these kind of adversarial losses for doing something which is called as a super resolution problem as well. So that's where I come to an end. So you can click on the same link tomorrow at 10 o'clock when we are supposed to start, and we'll continue with the next lecture itself. So thank you all.